Nuclear chemistry. Nuclear reactions involve the protons and neutrons in the nucleus, while chemical reactions only involve the valence electron. An important concept in nuclear chemistry is the idea of the mass defect. It is the difference between the mass of the nucleus and the sum of the masses of its individual nucleons. But how is that possible? Isn't the nucleus made up of the nucleons? Let's take helium for example. The predicted mass is 4.033 atomic mass units, while the actual is less than that. Where did the mass go? The mass went to a thing called the binding energy, the energy between the neutrons and the protons in the nucleus. This graph shows the binding energy per nucleon over the mass number. 56 is the mass number of iron, and as you can see, iron is stable and does not undergo nuclear reactions. Nuclear chemistry involves different particles and different types of radiation. There are three types of radiation: alpha radiation, beta radiation, and gamma radiation. They come from the helium nucleus, the electron, and the electromagnetic wave respectively. In order to continue our study of nuclear chemistry, we need to review isotopic notation, where the A is the mass number, Z is the atomic number, and X is the element number. There are three important types of hydrogen isotopes. First, there's the ordinary one, H11, which is just a proton. Then there's H21, which is proton plus a neutron called deuterium. Then H31 is known as tritium. Now we can dive into the different nuclear reactions. There are two types: fusion, fission, and then radioactive decay, which occurs under fission. Nuclear fusion brings together nuclei of small or lighter elements to form heavier elements with the release of energy. Solar fusion is a great example of this. Fusion that occurs in the sun. This is a three-step process, and as you can see, nuclear equations do balance in their A and Z values, their mass numbers, and their atomic numbers respectively. As fusion creates a lot of energy, scientists are looking in ways to develop it here on Earth so that we can harvest it. But for now, there's only one use that has been identified, and that is the nuclear bomb. Fission is the opposite of fusion, where fission is the splitting of a heavy nucleus into smaller isotopes and other particles and radiation. This is seen most clearly in nuclear power plants, where the uranium-235 is bombarded with a neutron to create U-236, which is very unstable, later decomposing into a lot of energy, krypton-91, barium-142, and other particles. This is a chain reaction that must be controlled. This is a diagram of a nuclear reactor, and as you can see, the control rod and the fuel rod help to make it controlled. Radioactive decay is a type of fission, and it is usually described in terms of half-lives. Different elements have different half-lives. For example, potassium-40 has a half-life of 1.25 times 10 to the 7 years, while radon only has a half-life of 3.8 days. This is a detailed diagram of uranium and its radioactive decay model, going all the way to lead. So, what are the main applications of nuclear chemistry? Well, there are three. First, there's medical. Second, there's war. And third, there's dating. First, medical. Imaging technologies have been made possible by nuclear chemistry as well as cancer treatment. War is the assortment of bombs including the nuclear weapon is a uncontrolled reaction, unlike nuclear power plants. And then dating. Carbon dating has a lot of historical use. Thank you everyone. Nuclear chemistry is super rad.